you can still do that. All right, so today's circuit session is about circuits in quantum algorithms. Why do we care about quantum circuits? What's the relation to quantum algorithms? So the power of today's quantum algorithms, of the near-term quantum algorithms, stems from running circuits. Circuits are things that we cannot do classically. So when we're looking at circuits, we're looking for different things. So instance circuits that are mainly circuits that are difficult to simulate classically, so that we have some part in our algorithm that is very challenging to recreate classically, or that cannot be recreated classically in an efficient way. So what is a quantum algorithm? Here I'm trying to give a working definition, not rigorously defining what a quantum algorithm is, but just that we all have the same base that we're coming from. All right, this notebook is available on GitHub if you want to have a look at that in the meanwhile. Yeah, so for the purpose of today, what we consider a quantum algorithm is an algorithm where some part runs on a quantum computer. Here, running on a quantum computer means running a quantum circuit or multiple quantum circuits. So an algorithm has an input, which can be of any kind. Then the algorithm creates one or several circuits, runs them on a quantum hardware, might apply some post-processing, and then gives you a result. Some circuits are iterative, which means that after the post-processing step, you recreate new circuits and you run it again. But essentially, you give some input, you get circuits, you do some processing, and then you get the output. You can't see my mouse, that's good, so I can use it later on. And as I said today, we will focus on the circuits part of algorithms. In particular, we will have a look at Qiskit circuit library can help us in building quantum algorithms and running quantum algorithms. Since we'll talk about it a lot today, I'll give a short recap on the circuit library in Qiskit. This was introduced 2 weeks ago in this session. It was introduced 2 weeks ago by Ali. So if you haven't checked that talk, you might want to do that. The circuit library is a collection of valuable families of circuits. Valuable can mean different things to different people. I think there are 3 main audiences for the circuit library. They are valuable because if you want to write an algorithm that might contain complex circuits, it's very easy to just grab the building blocks for these circuits from the circuit library and stack them together instead of rewriting all the algorithms yourself and all the circuits yourself. There are circuits in the circuit library that are of interest for research, for instance, for complexity analysis, because some circuits in the circuit library can be used to, or are conjectured to be useful for showing quantum advantage. But also, if you're just learning quantum computing, or if you're teaching quantum computing, the circuit library offers a wide collection of circuits that are common in many textbooks. You can just grab them and print them and have a look at them. You don't need to know, essentially, you don't even need to know Python or a programming language, because the circuit library is such an easy access, and you can just directly jump into quantum computing and circuits without any prerequisites. If you don't know the circuit library yet, I highly suggest that you play with it and have a look at that. So you could go to Qiskit directly. The circuit library is, if you're familiar with Qiskit, the circuit library is located at qiskit.circuit.library. You can check out the documentation. The link is posted here. You can check the previous session with Ali, or there's one pretty cool tool recently developed by James Weaver, which I'm going to show you. So this is a brief overview of what is in the circuit library. You can click here on the side, you can choose what circuit you're interested about. Then you have some information about the circuits, and here how they are, how you can call them from within Python. And then here you see the circuit. Yeah, bigger. Right, now it should be bigger. Right. Yeah, so you have some information on the circuit. Here you see the circuit itself, and you can change the options. You can change the number of qubits here, and then the circuit is going to be regenerated, and you can change the options here. Right. So moving on. Since we'll use it a lot today, the circuit library, I'm going to give you a quick recap on how you would use it. So say you're interested in a quantum Fourier transform. All you have to do is import the object called QFT from the circuit library. So you're saying from qiskit.circuit.library import QFT. If you want a 3-qubit QFT, all you have to do is you have to give it the argument 3, and then you can draw it and see the output. Here I'm choosing output equals MPL to have the nice matplotlib rendering. These circuits might have different options. For instance, the QFT has an option called approximation degree, where you can decide to not apply all of the controlled phase gates. Here you see where the phase gate, which here is not included anymore. This makes the circuit shorter and easier to simulate, but of course it's an approximation. And you can decide, for instance, to turn off the swaps in the end of the circuit. Also, you have seen that these circuits in the circuit library are normal circuits. So if you're interested, if you're familiar with the quantum circuits of Qiskit already, and you might know the operations that the circuit offers, you can choose these. You can use these methods, for instance, to investigate what object you have at hand. So, for instance, the circuit has a non-local gates method, where you can count the number of non-local gates. Non-local here means not a single qubit gate. So here we have 4 because we have a swap, and 3 controlled phase gates. You can count the number of total operations in your circuit, which gives you a dictionary with the number of Hadamars, the number of controlled phase gates, and the swaps. And since circuit can be inverted, you can just call QFT inverse and you get the inverse circuit. Right. So one method we will use a lot today is called decompose method. It is used to stack circuits together. You can give it you call it on an existing circuit, and you give it a new circuit that you want to attach it to, the qubits you want to attach it to, and whether you want the substitution to be in place or not. So for instance, say you want to create a new circuit with 2 components from the circuit library. What you have to do is you have to import a quantum circuit, say on 3 qubits, and then you compose it with a new object. So here I'm composing with a circuit called diagonal. Diagonal implements a unitary with where the diagonal is whatever I put in here. So here it would be a diagonal unitary with 1, 1, minus 1, minus 1 on the diagonal. And I want to apply it on the qubits 1 and 2. And I'm doing the substitution in place. Then I'm applying barrier, and then I'm composing with the QFT. You can see here I left out the qubits argument, which means that it's just going to be applied to the top qubits. Since I have here 3 qubits in the circuit and 3 qubits in the QFT, it just gets applied to all the qubits. So much for how you can use the circuit library. Let's have a quick overview of what is in the circuit library. This is not an exhaustive list. This is just a brief overview. So we have in the circuit library, we have a set of circuits called data preparation. These circuits encode classical data into a quantum state. This is used in machine learning, for instance. We have parameterized circuits, where These parameter circuits, they are used as models. For instance, they are used as an ansatz for the ground state of a molecule. These have 3 parameters that can be optimized in some iterative algorithm. We have arithmetic circuits, which perform arithmetic operations on qubit states, like, for instance, an addition or a comparison. We have generalized gates, which is, instead of just having your standard CNOT gate, you could ask for a gate that is controlled on 5 qubits and acts a Hadamard gate on 10 other qubits. Or the diagonal gate is also one of these generalized gates, which we just have seen. We have some circuits that are of interest from a complexity theoretic point of view. We have a quantum volume circuit, which is used to benchmark quantum hardware. We have a phase estimation circuit, and we have a quantum Fourier transform circuit. If you want a full list, I suggest that you go to the documentation, because this is not all that exists there. So now that we have the circuit library, how do we as users, researchers, or developers want to use it when running an algorithm? So going back to the definition that we had beforehand, the circuit library can come in 2 points. Some algorithms require circuits as inputs, as for instance, a variational quantum eigensolver. So here, depending on the application, you could go to the circuit library and see, okay, I have this particular application, what circuits are useful. Then you can grab these circuits from the circuit library and plug them into the algorithm. This would be the left arrow for the user. On the other hand, there are algorithms that use circuits internally, as for instance, the quantum phase estimation. So here you give a unitary operator and an eigenstate, and then the algorithm builds the phase estimation circuit. So you as a developer, instead of writing a new phase estimation algorithm, phase estimation circuit, you can just grab the phase estimation circuit from the circuit library. Let's have a small example. Namely the variational quantum classifier. So the variational quantum classifier is a classification algorithm. Given some classical input data and a data encoding circuit and an ansatz circuit, it classifies the training data and gives you a model to predict new data. So the data encoding circuit is used to map the data points xi onto a quantum state. This is like from machine learning, this would be what happens in the kernel. And then the ansatz is what is being trained. So you're stacking these 2 circuits together, and then you're tuning the parameters in your ansatz such that your data is classified correctly. Then you can stack all of these things together in the VQC algorithm and run it to get a result. If you want to learn more about that, then you can have a look at this paper here. So let's actually implement that and run that. So I know that I need from the algorithm, I know that I need a data preparation circuit. So I can go to qiskit.circuit.library. You can drop this part here. I just added it so that you can see that there's actually something called data preparation. It's not just a bag of circuits with random names and which you don't know where to use. So these are actually sorted, and you have in the documentation, you can see which circuit is useful for which purpose. So here I know I want a data preparation circuit. For instance, I could use the ZZ feature map. This is also introduced in the paper that I just referenced above. I can grab it and define it on 2 qubits, draw it, and see what comes out. I also need a parameterized ansatz circuit. This is in the module called local here. You can also drop that. And it looks like this. If I want to run the VQC algorithm, I have to import it from qiskit.arco.algorithms. I further need an optimizer, which optimizes the parameters. And then I'm doing some imports for plotting the data set and generating a data set. Here, I already did that for you because it takes a bit to generate this data set. If we look at the plot, then you see that we have a binary classification problem with 2 classes, A and B. A are circles and B are triangles. the full markers are part of the training set and the hollow markers are part of the test set. So now I can define my algorithm. I can plug in the optimizer, the data preparation circuit, the classifier, and the training data, and then I can run it. To run it, I need to choose a backend from R. Here I'm using a Quasm simulator, which will result in a shot-based readout of the circuits. And then I can predict the labels for my test points. So the output of predicted A should all be 0 because the test set, all labels of the test set here are A, which is associated to 0, and all of the points B should be labeled 1. And if I'm computing here the score, how many points I have been labeled correctly, how many have been labeled wrongly, I see that I labeled 19 out of 20 correctly. And I can also visualize that nicely here. So here in blue, you see the training data. In green, you see the test data that has been correctly labeled. And in red, you see the test data which was wrongly labeled. So in this case, it was only 1. So the circuits that we chose worked well. In principle, we can plug in any circuit in the VQC. So if you would not have taken the data preparation circuit, but something completely different, then the result probably would not have looked that good. So what algorithms use which circuits? I picked here 4 classes from the circuit library: the data preparation circuits, parameterized Ansätze, the basis change circuits, which is essentially the QFT, and the arithmetic circuits. I didn't put all of them because otherwise it would have been a too messy graph. The VQC algorithm, which we've just seen, uses data preparation circuits for computing the kernel, and it uses a parameterized Ansatz for the classification. A very similar algorithm is the quantum SVM algorithm, which is also introduced in the paper by Havlicek. And this just uses the quantum hardware to compute the kernel. So this does not need a parameterized Ansatz. Another important algorithm that we'll talk about later is the variational quantum eigensolver. This, for instance, only uses parameterized Ansätze. So you can see here is a brief overview of different algorithms. I'm not going to talk about them in detail because this will probably take up the whole hour. But feel free to look at that in the notebook. All right, so I earlier said that it is easy to build a quantum algorithm with the circuit library. Let's see if that's actually true. The algorithm that we will implement is the quantum phase estimation algorithm. The algorithm is provided with a unitary U and a corresponding eigenvector, and we want to find the eigenvalue to that eigenvector. Since it's a unitary matrix, I can write the eigenvalue as e to the 2 pi I times an angle. So essentially, we want to find the angle phi in here. In this example, we'll choose a unitary, which is x tensor x, and an eigenstate, which is one of the Bell states, namely 0, 0, minus 1, 1, divided over the square root of 2. The corresponding eigenvalue would be 2 to the pi I theta equals minus 1. So the circuits are easily computed in Qiskit using the quantum circuit class. So we have a 2-qubit unitary. We will apply an x gate to the 0th qubit and an x gate to the 1st qubit. And for the Bell state, we'll first apply an x gate on the 0th qubit, then an Hadamard gate to create the minus state. And then we'll apply a controlled x gate so that we have a 0, 0, minus 1, 1 state. We can compute the state vectors of these states using the state vector class of quantum info. There was also a very nice circuit session. I think it was the 2nd or 3rd one. If you don't know the quantum info package, I recommend you check that out. So I can create, to get the state vector of my circuit, I can say state vector dot from instruction and plug in the circuit. And then to apply the unitary, I can say evolve my state by this circuit. Right. So before, I need to laugh because I just saw somebody saying I cannot understand my accent. I thought German people have a very clear accent. I'm sorry if you cannot understand me. All right. So before, if you just look at the state vector is 1 over square root of 2, 0, 0, minus 1 over square root of 2. And if you apply the unitary, then you see that the state vector is minus 1 over square root of 2, 0, 0, 1 over square root of 2. So we see that our unitary actually applies a coefficient of minus 1. If you're not familiar with okay, now I see that this person is excusing, and my accent is very good. Thank you very much. I like the Qiskit community. It's very interactive and there's many nice people. But let's not get off track. So if you don't know the phase estimations algorithm, then I recommend you check out, for instance, the Quantum Computation and Quantum Information book by Nielsen and Zhuang. I've taken this picture out of their book. So what the circuit does is it applies it requires a set of evaluation qubits, and it has a secondary register for the eigenstate. So in the evaluation qubits, I will first apply a set of Hadamard gates, and then in the secondary register, I'm preparing my eigenstate, followed by controlled powers of the unitary. Finally, I will apply measurements on these evaluation qubits, and then the outcome will be mapped to a phase. So to build this circuit in Qiskit, all you have to do are a few lines of code. So here I'm using registers. We can also do that without registers in Qiskit, but if you do plots, it's sometimes nicer to have the registers because you can give them names. Right, so we will use 3 evaluation qubits, and we have a register for these evaluation qubits. We have a register for the unitary, and we have a classical register where we'll map the measurements into. So I'm defining my circuit on this evaluation register, on this unitary register, and on these classical bits. I'm starting by appending my belt state on the unitary register. Then I'm adding the Hadamars on the evaluation register, and then I'm applying the control powers. To apply the control powers, you can use the power and the control method of the circuit. So this is a quantum circuit, and I'm calling dot power 2 to the I, which returns me this circuit powered to the 2 to the I. And then the outcome is still a circuit, and I can control this. By default, this will give you a control on 1 qubit. Then I'm composing this control power onto my circuit using the IF qubit as a control. Finally, I'm applying my QFT, which happens here, which is also taken again from the circuit library, and I'm applying measurements. And once it's done, I can draw the circuit, and it looks like this. Yeah, this is what we wanted. Now I can execute the circuit. I can use since I have measurements, I'm going to use the Quasm simulator to get a shot-based readout. And I'm measuring 1024 times state 001. In the phase estimation algorithm, the outcome is mapped to a decimal using the binary fraction representation. So if I have a bits B0 and 1, which are 0 and 1, for instance, I'm going to map this to a number by saying, okay, B0 divided by 2, B plus B1 divided by 4, and so on. Here, we're measuring the state 0, 0, 1. The way the algorithm is defined, I have to swap this order first, which means I have the binary representation 0, 1, 0, 0. Hence, I have 1/2 plus 0 over 4 plus 0 over 8, which gives me 1/2 for the angle. And if I'm now plugging that into the exponent, I'm getting e to the pi I, which is -1, which is exactly the eigenvalue that we were looking for before. So we have successfully implemented the phase estimation algorithm. Now this was still too many lines of code. We could just use the phase estimation circuit from the circuit library, because before we've seen that it exists there. So the phase estimation circuit in the circuit library, you can import like that. You provide it with a unitary, and then it computes this circuit. Note that there's the eigenvector missing still. So to this essentially the same thing that we did before, we can use the phase estimation circuit, and the code is already much shorter. So here I'm not defining registers, but just giving the number of qubits that I want and the number of classical bits that I want, appending the Bell state on the bottom qubits, composing it with the phase estimation circuit, and then I'm measuring, and the outcome is that, which is the same thing as we had before. Right, and this was already pretty fast. So you see, if you're an algorithms developer that wants to implement a quantum phase estimation circuit, your code basically boils down to importing the phase estimation circuit, writing 5 lines of code, and the binary fraction logic. So this is why the circuit library is, this is one example of why the circuit library is so powerful, because writing circuits becomes second nature. Writing algorithms becomes second nature because it's very straightforward with the building blocks that you have. You don't have to worry about if the circuits are implemented correctly, because every object in the circuit library is tested. You can look up the tests, see if they make sense to you, and so you have a trustworthy source of circuits that you can use for your work or for education. Right. So much about building a quantum algorithm. The next thing I want to talk about is about how circuits can be used as an input. And here we're going to look at the parameterized quantum circuits. The first example that we'll look at is the max-cut problem. So the max-cut problem is the problem of finding a largest possible cut in a given graph, which means, in normal words, I want to find, given a graph, I want to find a path through the edges which separates all nodes into 2 groups and gives me, and where I'm cutting as many edges as possible. So this is very well explained in the Qiskit textbook. Just look for Qiskit textbook max-cut or Qiskit textbook QAOA. I think we can share the links later on in the description of this video. There's a very nice Medium article, which we'll also share, or if you want a more advanced treatment, then you can have a look at this paper here. To generate a graph, we can use NetworkX in Python. We'll have a 4 nodes graph with some edges here. Yeah, a very simple graph. The max cut for this graph would look something like this. So I would have nodes 0 and 2 in one class and nodes 1 and 3 in one class. If I'm associating the first class with the label 0 and the second class with the label 1, then my solution would be 0, 1, 0, 1, or 1, 0, 1, 0, because this is a symmetric problem. I don't care whether 0 or 1 are in class 0 and 1, 2 in class 1, 3 in class 1, or the other way around. I just want them to be separated. To run this problem, I can use the variational quantum eigensolver, but for this, I need to encode the objective function into a Hamiltonian. This is explained in the reference that I just gave above. I'm not going to go into detail about that, but the operator looks like that. Here I'm using, if you haven't seen this notation, this is Aqua's operator class. So the caret here means a tensor product, and I and Z are the Pauli I and Z operators. So now the question I want to talk about is which ansatz you want to use in the variational quantum eigensolver. So the ansatz that you give tries to approximate the solution state, and the parameters are tuned until the objective function is minimized. Ideally, we want to have a full access. We want to have access to all the possible solutions. We don't want to have an ansatz which only gives us possible solutions 1, 1, 0, 0 and 0, 0, 1, 1. I want all possible bit strings. On the other hand, I also want some ansatz which has few parameters, because these parameters are optimized by a classical optimizer, and many parameters will take a long time and will be difficult, or maybe the optimizer will not find a minimum. So here I'm trying to find an ansatz which just covers my solution space. For instance, here I know that I don't need complex amplitudes, so I'm looking for a circuit which has only real amplitudes. Luckily, the circuit library provides you just with that. We have the object called real amplitudes. It's called like that because it applies RY gates and CX gates and neither of them introduces a complex amplitude onto my qubits. Again, I can check this with the state vector object. This circuit has 3 parameters, which I need to bind before I can simulate them. So here I'm calling, so ansatz is a quantum circuit, and I'm calling assign parameters. And here I'm just plugging in a list of random parameters. And then if I compute a state vector, I see that indeed it only has real amplitudes. This is not a random check where this by coincidence has real amplitudes, because I'm here using random parameters. This is actually a property of the circuit. Right, so let's run the algorithm. I'm importing the VQE algorithm from Qiskit Aqua and importing an optimizer. I'm defining my ansatz, which we decided should be real amplitudes on 4 qubits. And here I'm choosing 4 repetition. The repetitions tell me how many times I repeat rotation layer, entanglement layer, rotation layer. Here's 4 times. This also gives decides the number of parameters in the circuit. Then I'm defining the VQE algorithm by plugging in the Ising operator, which we defined above, my ansatz, and the optimizer. And then I'm running this whole thing on a Quasar simulator. The outcome is this. So this is what what was sampled in the algorithm. I can plot this using plot histogram from Qiskit.visualization. And I see that the most likely state is the 1010 state. And this is perfect because this is what we identified as one of the possible solutions before. So our algorithm worked. In principle, I don't have to use these real amplitudes. As I said before, it's desirable to cover the solution space and still minimize the number of parameters. Well, there's also more things that the circuit should satisfy, but we'll talk about this in a minute. Right, so I could also say, okay, I'm going to use this circuit called efficient SU2, which has RY rotations and RZ rotations. It's called efficient SU2 because the single qubit unitaries that are applied are in the group SU2, and efficient because it's too local. Too local means that I only have interactions from one qubit to another. I don't have 3 or 4 qubit gates. And you see that if you count, maybe this is too small, but if you count here the number of parameters, you see that this goes from 0 to 31. So I have 32 parameters. And this circuit gives me complex amplitudes. So I have twice the amount of parameters, and I'm covering a huge space, which I'm not even interested in. So this probably works as well, but takes some much more time, or the optimizer might not find it. And here I ran it. Oh, you cannot see this. Well, okay, so let me tell you what it is. So here we have the 110 state, and here we have the 010 state. So this is still the correct solution. This is the wrong solution. You see that the algorithm still somewhat found our solution, but the optimizer clearly had problems because it almost didn't converge. So this is a cool object that I want to talk to you about a little bit, which is called a two-local circuit. The two-local circuit is a template for hardware efficient circuits. Here, hardware efficient means that they are only 2 local gates in there. Two-local object takes a number of qubits and takes what you want to use as rotation blocks and what you want to use as entanglement blocks. Then it takes how often you want to repeat your blocks and what kind of entanglement you want to use. This is easiest explained in an example. So I'm importing this object from the circuit library, and I'm telling it I want 4 qubits, I want RY rotation gates, and I want CX entanglement gates. And what I'm getting out is this circuit. So by default, it's using a full entanglement, which means that every qubit is entangled with every other qubit, and 3 repetitions, which means that I have 1 rotation layer, then an entanglement layer repeated 3 times, plus the final rotation layer. This final rotation layer is always applied because if I wouldn't, then I could just take these C0 gates and do them with classical logic. So I wouldn't gain anything from just final C0s. Right. So you can do many things with this object. For instance, you can give a list of single qubit gates. If you want Rx gates and Ry gates, you can provide it with a list here. And you can, for instance, also change the entanglement. So instead of full entanglement, what we had before, now we're choosing linear entanglement, which means that every qubit is entangled to its next neighbor. Other options are, for instance, circular or SCA. SCA is a fancy way of circular with some additional shifts in between every block. This is documented if you're interested in the documentation, of course. So this is a convenient tool to access standard circuits, because you can just give it a list of the standard gates that you want: X gate, Hadamard gates, Rx, Ry, CRZs. But you can also give it custom single or 2-qubit circuits, so you can plug entire circuits in there. You can choose custom entanglements where you're concretely specifying which qubit should be entangled with which qubit. You can even change the entanglements through the blocks. You can change the number of repetitions. You could couple parameters. So for instance, before we had a circuit where we had 32 parameters, which is a lot. You could instead go ahead and say, hey, I want every parameter to be the same as the next 5th parameter. And if you want to go really fancy, then you can use the nlocal version of that, which is called qiskit-circuit.library.nlocal, where you don't even have this toLocal restriction anymore. So a bit more advanced example would be here. Now I'm using a custom circuit as an entanglement block. So I'm defining here my 2-qubit entanglement circuit on a parameter P. So this is Qiskit's way of doing parameters. I'm applying a swap gate, and then I'm applying an Rx gate with parameter P on qubit 0, and a Y gate on parameter P on qubit 1. I'm defining a single qubit gate on which is just a single qubit circuit. I'm applying a T gate and a Y poly gate. And then I'm defining my toLocal circuit on 3 qubits. One of the single qubit gates is what I defined here. And then I'm also throwing in an Rx gate. And as entanglement, I'm using my entanglement circuit from above. I'm using circular entanglement, which means that it's linear entanglement, but the top and the bottom circuit qubit are also connected. Just one repetition, and I'm inserting some barriers for visualization purposes. And the outcome is what you can see here. So I have my T gate, my Y gate. This is my custom circuit that I've provided. Here I have the Rx gates. And here I have my entanglements. So here I have one entanglement gate, a block, another one, and another one. And since I used here the same parameter P in these both gates, again, it might be too small, but here I have the same parameter in this bottom and in this top and in this bottom gate. But there's virtually no limitation set. You can pretty much do whatever you want. So it's nice to have this this object where I have a lot of freedom to create ansatz. But in a sense, I'm interested in what works well for my application. So the answer for what works with your application is, we have some idea for some applications, but in general, we don't know. And this is an active field of research. See, for instance, this paper here, where the expressibility and entanglement capability of different ansatz is investigated. And one circuit, for instance, that's been proposed to work well because it's very expressible is this circuit 6 from this paper, where we have Rx and Rz single qubit gates, and we have an entanglement block consisting of multiple controlled X rotations. So to create this circuit with the toLocal object, I'm telling it I want Rx gates and Rz gates as single qubit rotations, and I want CRX gates as entanglements. Then I have to create this entanglement structure that we've seen above. Probably there's some functional way to define that as well, but I just looked at the entanglements and I've written them in here. So I have a list of target and of control and target qubits, and this is the outcome. So the only difference to the circuit before is that these two middle Rx gates are swapped, but this is because they're commuting, and this is just Qiskit's way of showing that. Right. So now that we did this excursion on what circuits and what Ansätze you can create yourself, you can do whatever you want there, and then you can plug it in the VQE. As before we had the icing, here we had the real amplitudes, but we can just use this and then plug in the optimizer. Essentially, if you want to come up with your own circuit and you don't want to use the NLocal or 2Local, you can also do that. So the algorithms also support any circuit as input. So say I want to create my own circuit. I'm just going to, again, create a quantum circuit. I'm going to create 16 parameters. I'm applying a rotation layer of Y gates. Then I'm appending a QFT. Again, Y rotations, another inverse QFT this time, and more rotations. This will look something like this. And you can also use that. I'm not saying that this is a circuit that would work. The algorithm would accept it and it would run something, but if the outcome would be sensible, I don't know. But if you happen to find a circuit that works well, then you can add it to the circuit library. You can say, hey, I found a circuit which works very well for the max cut problem. Here, there it is. You can use it. And this is one of the key features of the circuit library, that it is extensible. As I said before, we have these tests already. So if you come up with a new circuit, you know that there are already tests. So you just have to write your circuit. And the more circuits we add, the easier it will be to extend this library, because we can use circuits that are already in there. We know we already have a feeling for what circuits are useful. So as a quick summary, it is important to choose the right ansatz for your quantum algorithm. The circuit library offers a set of standard ansatz circuits already, but it also offers tools to build new ones, for instance, using 2Local or NLocal. But essentially, Qiskit's algorithms run on any custom circuit. So you're only limited to circuits, unitary operations. So this was a optimization application, and I want to quickly talk about another application from chemistry. In particular, a application where we're trying to find the ground state of a molecule. So if we try to approximate the ground state of a molecule, we want complex amplitudes, because in principle, the wave function amplitude circuit from before. What we could use, for instance, is a circuit called, the efficient SU2 circuit that we already have seen before. If we look at the state vector, we see that it has here complex amplitudes. Ignore this cell. This is because of a bug on my laptop. Right, now we can look at the H2 molecule, and the Hamiltonian of the H2 molecule can be mapped onto this qubit operator. For people with chemistry background, this is a parity mapping with the 2-qubit reduction. Right, we're using the LBFGS B optimizer, and we want to reach an energy of around -1.8. And we're using a quantum simulator backend, and then we can run the algorithm by providing it with the H2 operator, our ansatz, and the optimizer. And we see that we're getting something somewhat close to what we want. However, there's a different approach in chemistry which might be of interest. So classical chemistry has a long history, because it's a thing that's very useful for in pharmacy and in research. So in classical chemistry, the UCCSD method is sometimes considered the golden standard. Here, UCCSD in brackets T stands for unitary coupled cluster single and double excitations with a perturbative treatment of triple excitations. And this gives us a recipe for a ansatz wave function. Instead of creating new wave functions, we could also say, hey, there is already this well-founded literature in classical chemistry. Let's use that. For a background on this, you can check out this paper. Yeah. So you will remove the perturbative treatment of the triples and just use the CSD single doubles excitations. this circuit is currently not in a circuit library. It's still in Qiskit.chemistry, but will probably move at some point to the circuit library. Practically, this just means that we have a slightly different syntax, and we have to call here construct circuit. The UCCSD takes the number of orbitals and the number of particles that I have. So in the H2 molecule, in the operator representation that we had before, which uses the minimal basis STO3G, has 4 orbitals and 2 particles. So I'm constructing this, I'm calling UCCSD with 4 orbitals and 2 particles, and what I'm getting out is this circuit. Now I can run VQE with this circuit, and I'm seeing that I'm getting something already closer to -1.8. Cool. So this worked well. Why aren't we just always using UCCSD? Well, it worked well for this system, but this is a H2 molecule, which is a fairly small system with the most basic basis set that we can use, or one of the most basic basis sets that we can use. This is not something that we would actually use in practice. So let's look at some larger systems. This function here defines can define my Hamiltonian and gives me the number of orbitals and particles. In the interest of time, since I only have 10 minutes left, I'm not going to go through that in detail, but feel free to look at the notebook and the documentation of Qiskit. So if I ask for the H2 Hamiltonian and the number of particles and orbitals in the STO3G basis, what I'm getting is this operator. If you remember, that's exactly the operator that we had before. So this is where it comes from. And as I said, I have 4 orbitals and 2 particles. However, if I'm now changing to a slightly more difficult molecule, for instance, lithium hydrate, still in the minimal basis. I ran this before because it takes quite a while. I'm getting an operator on 10 qubits and with a lot of summits. I'm not sure if you can see my scroll bar here on the right, but it's a lot of summits. And now I have 12 orbitals and 4 particles, which if I plug that into UCCSD, so I'm plugging the number of orbitals and number of particles, I'm getting a circuit, an answered circuit on 10 qubits with a depth of 8,500 gates. So depth is the number of non-parallel qubit operations. And this is far out of reach of anything that we could do on hardware. Our qubits are long gone before we can apply 8,500 gates sequentially. So this is the problem of this UCCSD ansatz. It's classically motivated. It works well there, but we don't have this restriction that we have right now of that we need shallow circuits with ideally a short depth. I mean, this probably would be okay to simulate, but still very expensive. Right, so is there a middle ground? The answer is somewhat yes. So before we use the parity mapping, but there's another mapping which, so for people that are not chemists, this is a mapping which takes your Hamiltonian in second quantization to a qubit Hamiltonian. But the important part is that there's a mapping where we can associate a qubit set of 1 with an existing particle. Since the total number of particles should be conserved, the ansatz wave function should conserve the number of 1 states. For instance, 0 state should always stay in 0 states. 1 state should stay in all 1 states. But if I have, for instance, a 1-0 state, that can interact with the 0-1 state. In a circuit library, we have the excitation preserving circuit that does just that. So the circuit looks like this. I have RZ gates as single qubit gates, and I have RXX and RY gates as entanglements. RXX and RY apply a joint rotation over the XX axis. Again, I'm referring to the documentation for more detail. So here, I have to ask for a slightly larger Hamiltonian because I need to use the Jordan-Wigner mapping, which doesn't allow me to do a 2-qubit reduction. But this is why I have reduction faults here. But the operator that comes out of that has 12 qubits before we 10, so this is still pretty close. But the depth is reduced from 8,500 qubits, 8,500 gates to 94, which is something that is way more feasible. Also, the number of parameters changed significantly from 90 to 250. So here you see we have a trade-off between different circuits, and we need to know which circuit we want to use for which application. All right. So bottom line is the circuit library has this large set of circuits that I can use for different things. I can build algorithms with it. I can use it to run algorithms because I have a well-tested collection where I know, okay, this circuit works well for this application, this circuit works well for this application. If I don't know which circuit works well, I can still just go to the circuit library and test several ones, see which one works best. The circuit library is called library for a reason. It's like a library. You can be an author, you can add new books. In this case, you can add new circuits. If you need concrete ideas, there are loads of arithmetic circuits. You can do additions in different ways. You can add more basis chain circuits. We only have the QFT right now, but you can add a discrete wavelet transform or a cosine transform or any other circuits that you'd like to share or that you found to be useful. You can, so many of these circuits are based on a theoretical foundation. So there are probably efficient ways to test these circuits. You can contribute by adding tests. If you know of an optimized version of, for instance, a 5-qubit Fourier transform, you can also contribute that. You can add more options to the circuits. Say I'm adding a 3-local circuit or whatever. Yeah, feel free to contribute. I'm going to share the link to the open issues or to the circuit library Qiskit in YouTube later on. And now I have five minutes left for questions or more material. So I'm going to try and scroll through the questions. If you have any, feel free to type them now. How long is this going to last? Well, 5 more minutes. Can I modify circuit? Yeah. Can I modify circuits by adding or removing gates from it? Adding gates is very easy. You can just say circuit.x.y, then give the qubit index. Removing gates is possible. There's it's not such an easy way to remove the gates because the problem is, like, how would you, say you have a circuit with 10 gates, or maybe I can have a circuit somewhere. Like, how would you tell Qiskit to remove, especially like write this RZ gate somewhere in the middle? It's difficult to remove these gates without having a coordinate system set out. It is possible. You can go into the circuit and see what operations are in there, and then you can remove them from the list of operations. But yeah, it's not straightforward. Well, it is straightforward, but it's not like a method on the circuit. Can we choose the order of the composition? Yes, you can. There's an argument called front, which will append a circuit on the front. This was added though in the latest version of the master branch, so you should install Qiskit from source. Does it support QAOA? I think you refer to the MaxCut problem, and the answer would be yes. There's QAOA in Qiskit.arg algorithms. And there is an optimization module, which will be given an introduction about in 2 weeks. Does it help to view intermediate circuit? I would say a lot. The circuit defines what, it doesn't help to view it, like to physically see it, but it probably helps to do some tests on it to see what states it can reach, to see how many parameters it has. Because basically the outcome of your algorithm depends on that and how fast it will be. All right, more questions? Do we have a Slack community? Yes, this question was already answered. Qiskit should publish a book and make it available. There is a Qiskit textbook. I don't know if you mean that. Oh yeah, that was already answered as well. All right, so if there are no questions left, it's too late to start a new topic. Thanks for listening, for tuning in, and see you all maybe in some Qiskit event once that the situation outside has calmed down again. Have a nice day.